Okay. Now let's recap. Where, like, raise your hand again if you're like, yeah, I don't, this seems like, what? Why? Why is it different? A lot less people this time. But it is seemingly different. But in the end of the day, it's actually not copying the list. What it's saying is this is an alias for. This is another name for that one single list that exists. And this is how it's working for those things that are like, well, how am I going to store a big string? Now, strings are a little funny. But if I have a list, you know, I want a list of integers, I know how much space an individual integer takes up. But if I have an arbitrarily long list, I don't know how much RAM I'm going to need. So in those types of scenarios, it's terrible. Geesh, that hurt my ear. So we end up with an alias. We end up saying, okay, no, this is just another name for that same thing. So you're asking, but why didn't it work that way with B? When I said A equals B, it didn't make A another name for B. It copied over the contents of A and put it into B. Well, actually, that's what's happening with these lists. Someone came up to me after and asked, like, well, what if you really do want to make a copy, though? Well, there are a bunch of ways to do it, and the easiest way in Python is to say, give me everything from A. This is the shorthand for saying give me everything from the beginning to the end, and put it in B. So this will make a copy. There are other ways to make a copy, but this is the easiest way, I'd say, in Python. So if you really want to, there you go. So yeah, let's do this activity. Real quick, it shouldn't take very long. Create a list name, I mean, whatever you want, and then make an alias, and then make a copy of the list named lcopy. Prove to yourself that one is an alias and one is a copy. Go ahead and do that now. I'll give you like 3 minutes to do that one. And just to get prepared for what I'm about to talk about next. Is everything okay? That may have been the most difficult escape I've ever seen. That noise is also annoying too, isn't it? Any idea what that one is? It's the blinds? The train. Ugh, the train. All right. If you see it and you think you could fix it, give it a go. If you think like, yeah, there's no way, just leave it alone. It's fine. Yeah, but it's hot in here. How many computer science students does it take to figure out? Probably just him, you're right, but it took enough to be like, yeah, just go. It was that case of like, you, me, no, shoot, who's gonna? Yay! All right. Now, hopefully it doesn't start over there. So I made a list. Okay, raise your hand if you're done that activity. Raise your hand if you are thoroughly convinced that you did what I asked you to do. Not everybody, so let's just go through this one together. So I have a list. And then I say make an alias for it. Well, the alias is easy to do. Equals a list. Okay, done. This is now an alias. I could keep doing this. And to prove it, if I say a list at location 1 equals 99, and then print alias okay, it's running, initializing. There we go. So I used a list. I used the a list variable name to index that list and then make a change to that one single list. Then I am saying, all right, print out the alias list. So this does not say alias list, it says a list. Yet when I print out alias list, it made the change. So now we know it's an alias. We know that both a list and alias list are variable names that gets us to the one same single list. Imagine I have a variable called right hand and a variable called left hand. And they are both pointing at you. Okay? And I say right hand, put up your hand. Just put up your hand. You. Yeah, you. You. Put up your hand. Up really high. Yes, you. See, I said right hand, do it. But through the optics of my left hand, it modified the one single thing. There's only one list. There's only one you in here. But I had two things, right hand and left hand, referring to you. So now we want to make a copy. The easiest way to make a copy in Python, is to say a copy equals a list like this. Because if you remember, if I say a list at 4 to 7, that'll give me the indexes 4, 5, and 6, right? But if I just do a regular colon, it means all of them, from the beginning all the way to the end. And it gives that back to me. So that actually does make the copy. It returns a copy of that list, and then I save it in a copy list. Then I can say a copy list at index 1. Let's put that back, let's make that a Z now. And then print a list. So look, now when I modified a list, or pardon me, now when I modified a copy list, a list was left alone. And then I can go print a copy list, but this one's modified. The takeaway from this is not that I need to memorize this right now and know this immediately. Yes. Yeah, you do need to know this. But the point of this is be aware that there is a huge difference between an alias, when you have an alias, and when you have a copy. And this right here is going to be the bane of your assignment 3. So keep this in mind. Really? When I say a list equals this list, right? And I ask you the question, well, okay, now what is a list? And you're like, well, it's that list. No, it's not. A list is the variable that gets you to that list. It kind of tells you where to go to get it. So let's go through a bit of an example here of how this computer works historically. And this is generalized, this is high level. I'm not getting into the nitty-gritty. But let's think about our computer, and our computer has RAM, random access memory. This is like the workshop table of your computer. If we have a variable that we need to store, we store it in RAM, typically. If we have data we want to store, we'll store it in RAM while the program's doing its thing. And then when the program's done, it doesn't need that RAM allocated to it anymore. But we have RAM, and we have a lot of it. Back in the day, we didn't have as much, but now we've got a lot of it. Who here knows how many gigs of RAM their computer has? How many you got? How many you got? Is your hand not up? Nope. What do you got?
16.
How about you? 32. Wow, how about you? 16. 16, that's a lot.
16.
Yeah, 16. Wait, what did I say? Did I? Well, whatever. That's a lot. 16 what?
16 gigabytes of DDR4. That's not a lot of RAM.
16 gigs of DDR4 is a lot. Well, relatively speaking, yes, absolutely yes. Now, if you've got like a supercomputer where you have crazy amounts of RAM, that's one thing. But yeah, 16 gigs of RAM, that's a lot of RAM. To put that in perspective, let's talk about how many zeros and ones that means. Who here knows they're like metric prefixes reasonably well? Decently? Now, for simplicity here, I'm going to simplify, because in computer science, we've actually cheated quite a bit and are relying a little bit in terms of what like kilo, mega, giga, tera means. And I don't want you to get confused between gigs, or pardon me, your RAM and then like your like disk drive. Disk drive is like long-term storage. That's where you save all your photos and games and applications and stuff. RAM is the working memory of it. So if I have 1 byte, that's 8 bits, right? If I have a kilobyte, that's 1,000 bits. Technically, it's 1024, but for simplicity, it's 1,000. If I have a mega, that is 100,000. And then if I have a giga, wait, 1,000, a mega is a million, pardon me. 1, 2, 3, 4, 5, 6. Yeah, I was right. Mega's a million, and then giga's a billion. We have a billion. I don't know why I'm typing it in here. I was going to do the math, but whatever. We have a million. 1 gig is a million bytes. No, a billion. 1 gig is a billion bytes, which is 8 billion bits. How many nibbles? Oh, you don't remember?
Double that?
Double?
16, isn't it?
No. A nibble isn't as big as a whole byte, right? It's only a nibble. It's 4. So it's 4, whatever. It doesn't matter.
Double whatever your number is.
No, it's half. Half. So,
How many nibbles is double how many bytes though?
yeah, if you go that way, yeah.
That's the way I was going.
I gotcha. So, we have a million bytes. A billion. I keep saying, and then 16 billion. That's a lot. 16 billion, and then if you times that by 8, that's a lot of zeros and ones, right? So we tend to like to think of our RAM kind of like a list in the sense that each memory location has an address. Like houses on the street, like indices in your list, they have an address. You can store the information, but the information is stored at a specific address, memory address. And we like to think that, oh, it goes on forever. In practice, well, no, it doesn't. But, there we go. So here is a snapshot of some RAM. We've got memory address 124, 125, 126, 27, blah, blah, blah. And let's just, it keeps going that way and it keeps going this way, okay? By the way, in reality, we like to think of RAM, or we actually use hexadecimal. Remember what that is? Nope. That's when you count 0, 1, 2, 3, 4, 5, 6, 7, 8, 8, 9, A, B, C, D, E, F, where F means 16. But if I write F, I can get 16 with only one symbol. Doesn't matter. So, let's talk history. We have lists. Lists are fantastic. Lists are amazing data structures. But if we go back in time, we have the more simple idea of an array. And the array really is that, like, okay, if I want my array to store integers or something, or characters, whatever, doesn't matter, simple types, primitive types, maybe it's a float, maybe it's a Boolean, I will say, okay, how much RAM do I need to set aside? Well, how big do you want your array to be? Historically speaking, unlike lists, arrays have a fixed size. If I say I want an array of size 4, like this row here, great, I have room for 4 integers. If I want to put a fifth in there, I can't. I'd have to make a new array to store that one. So I've got these arrays. So what do we have here? Above, we got an array of length 8. So instead of an array, we have arrays of fixed length, list, fixed size, no fancy methods. Yeah. This will all work the same for lists technically, but it's far easier to explain with simpler arrays. Okay, so we have an integer called x, so it's not an array. And if I say something like x equals 17, your operating system goes, okay, I need to find a chunk of RAM to store this value, 126. Why 126? I just picked it. And I'm going to store in it the value 17. It's an integer. And I have the variable named x, which is just a label for like that memory location, where I can find the value I want. So it's like I made a box, label x, and I put a value in it. Great. But really, the x is like just the label for that thing. It's a lot easier to work with variable names as opposed to remembering all these memory addresses and doing all that stuff. So we have these variable names. We store the value. Great. X equals 17. So something like store the value 17. Yep. Okay, great. Now if I say something like y equals x, all right, the computer's going to go, oh, we've got another variable called y, so I need to set aside some RAM to hold on to that. So I picked location 129. Why? Because. So we've got location 129, and then we copy over the contents of x, which is what? Yell it out. 17. Who said 32? 17, of course. So we copy over the contents of x and put it into y. So they both have 17. Okay. So everybody say the following with me. I'll say it once and then you're going to say it with me. I copy over the contents of x and put it into y. I copy over the contents of x and put it into y. If you think I'm being mean, no, this is for your own good. So now let's say I want an array to have A, B, C, D, E, F, G, and H in it. All right, let's be quiet and listen. I want to store an array. But unlike the case of, okay, I just need to go set aside some RAM for a number 17, where the computer's going to go, sit there. Great. Arrays are different. We need to find a chunk of contiguous memory big enough to hold on to that information. And the computer goes, okay, fine, you want an array of size, whatever that is, 8? 1, 2, 3, 4, 5, 6, 7, 8. Yep. All right. We'll start at memory address 677. Why? Because. So in 677 we have A, and then 678 we have B, then C, then D, and so on. So each of those values are stored in the consecutive chunks of RAM. And I want to emphasize this is idealized. There's more complexity to it than this, but this is the high-level important idea. So we can't shove a whole array in one chunk of memory. We need to have like a nice, good enough, big enough size of memory. So now we kind of have an issue though of like, well, how do we refer, like, how are we going to hold on to this information? Because it's not that I need to store A, B, C, D, E, F, G, H. I need, like, that's great and all, but like, what should I label there? Because here it was simple. I've got 17 and I labeled it Y and X and whatnot. Arrays, like, it's a little different. So we need to come up with a good, handy way to deal with this funny situation. So we store it in a chunk of RAM somewhere. But what I do, if I said something like Z equals A, B, C, D, E, F, G, H, the computer goes, sets aside that chunk of RAM over here, starting at 677, and creates a new variable called X, nope, Z, a new variable called Z, and what we actually store in it is the information we need to get to that array. It's kind of like a middleman. It's kind of like you're asking me to tell you how to get to your friend's house instead of you just going to your friend's house because it's more complicated that way.
I'm curious, how does it know when to stop?
How do you mean?
How does the thing know when to stop the list of the array?
The array?
Do you know the address that puts in Z, or
Only the starting address fits.
how does it know when it's done?
Well, it depends on the programming language.
685.
It depends on the programming language. So this is a far more complex question than you probably realize. Because in reality, in some languages it'd be an object and the object holds a lot of other information. But if we're speaking like old school arrays, it doesn't know when it ends. It doesn't. It just goes, oh, size 5, great, I need something big enough 5. And then if you say, okay, well, we'll come back to this. In fact, maybe I'll show you real quick after. So, if I said Z equals this, it goes and finds a chunk of RAM that we can put this in. That's over here, we're happy. And then it creates a variable called Z, but Z doesn't store that list. This is not the list. It's the information that I need to get to that list. Any questions about this? Be honest, ask the questions if you have any questions. Yes?
Is it basically just a string of extra sets though?
Pardon, say that again?
It's just a string of extra sets, right?
With extra sets? Like
Yes.
steps?
Like rather than the variable goes to it, the variable goes to something that takes it.
Yeah, but it's not even a string. This is how strings works too, classically speaking.
Yeah.
Because I would put a single letter in there instead of like a thing. So this is an array, but a string is kind of like an array. In fact, really classically speaking, depending on the programming language, they are the same thing. It's just a string is an array of characters. But anyways, good observation nonetheless. Other questions or anything? Because that was a good observation. Okay, so we have, and you got to remember, this is because it's not like a simple primitive type. With these primitive types, we're really happy. We know how much room they take up, and I can just shove them right in one seat. Great. As soon as we're in a scenario where we can't shove them in one seat, we need to be creative. This is how we're going to work. So, the word we use to describe this situation will depend on a couple of things. It'll depend on the programming language you're using. It'll depend on what it actually really means in that programming language. But if you're using C++, we would call this a pointer. Yeah, we'd call it a pointer because it points to that memory address. If this was a language like Python or Java, we call it a reference. But the problem is reference means something very different in C++, so it's just a nightmare of nomenclature. Sorry, pardon? It's not that bad. Because they are so different that you can't really mix them up. Well, that's kind of true. So anyways, take 1 minute, look at this picture, see if you can explain why we start counting at 0. Oh yeah, I know I've explained this a bunch. Why do we start counting at 0? Yeah, that's one reason.
Because it's how many steps you take.
Because it's how many steps you take. It's like we're doing arithmetic. go to address 677 plus 0. Go to address 677 plus 1. Well, what's 677 plus 1? 678. Exactly. So there you go. Now, earlier we saw lists work a little funny. They have this alias scenario. And you might say it's acting different than the primitive types, because with the primitive types, I just copied over the contents of the array. No. I copied over the contents of the memory address. Y equals x, I copied over the contents of what's actually stored at the memory address that x gets us to, and put it in a new memory address that we're labeling y. Right? And I made you all say it. We copy over the contents of x and put it into y. And that seemed reasonable. But as soon as we saw this funny alias thing, it seems like it's not doing that. But it is. It's doing the exact same thing. If I come along and say w equals z, let's see what happens. I create a new variable w. I copy over the contents of z, which is the address 677, and put it into a new memory address 6. I put 677 in the new address and label it w. Everyone say it with me. I'll say it once and you're all going to say it with me after I say it once. We copy over the contents of z and put it into y.
You mean W?
Yes. We copy over the contents of z and put it in w.
You mean W?
I said w the second time. So it's the same. There's nothing different happening in terms of what's getting copied. The difference is, what is the actual thing stored in that memory address? Sometimes it's a value, like 17. Maybe it's a character. Maybe it's a Boolean. Maybe it's a float. Or maybe it's a memory address. Maybe it's the information you need to get to somewhere else, which is the case we have here. So you will see that both of these memory addresses, z and w, get us 677. And this is why it's an alias. Because we never made a copy of this information with this syntax here. There is no copy here. There's one of these. We copied over the contents of z, but z's the memory address, not the list. So whenever I say something like z equals this new list, that's never really true. Z equals the information I need to get me to that new list. Z is a reference to a list, not a list. I will be using the words, oh, okay, we'll make a new list, put it in Z. That's not accurate. I'm using those words just for simplicity. But in reality, we can think of it as, well, no, Z's only the information that gets me to that other thing. Any questions about that? I'd be shocked if there are none. So I should expect to see a couple of questions. Yeah.
So when you use the variables in just one value, like say x is equal to 17y, y is equal to x, that's actually copying over the physical value 17. And so if we change it, if we get a value of x after that, y would still be equal to.
Exactly. Think about what it is physically. And I like the word you said there, like the physical value. What might seem like a funny thing. You're like, well, it's a virtual value. Well, really, there are physical low voltages and high voltages in there somewhere that mean 17. There is a physical representation. Yeah.
Is this an array or a list? I'm sorry.
This is an array, but it's you can think of it with your list hat on. Technically, are you in 162? You'll learn all about lists and how they actually work there, because it's more complex. But with an array, they're a fixed size. So if you're like, I want an array of size 10, great. But if you have an 11th thing you want to put in there, you're out of luck. So we kind of have this like wrapper thing around arrays that say like, well, if that ever happens, just make a new array that's bigger, copy over the contents, and then add a new one. That's how lists are working. So it's the same idea. And you have a follow-up?
Yeah, have we been using arrays all semester instead of lists?
No, you've been using lists, but under the hood, it's going to be something more like an array, technically. Yeah. And yeah.
I can assume strings also slightly differently just to computer, since we can edit a list in a way that we can edit strings.
It depends on the programming language and how it's designed. So all of this is very classically speaking, and all of this is assuming that we strip away a lot of the nuance between different programming languages. Because strings in many languages like Python, Java, and modern C++ will have like a special whole object thing that manages the string. But if we go like way back to 1970 something, we're using C and we want a string, we do only just have an array of characters. But the one trick we did with strings back then is we'd add a special null character at the end of the string, and that would be the end. Now, to get to the question you had, let's have fun and do stuff we shouldn't do, okay? I always like doing this. Hopefully, it'll open properly. I'm going to open up and program in a language C/C++, okay? And I'm going to make an array in that language. I'm going to try to at least if cline opens. Did I even click it? Oh, something. Yeah, okay, something's happening. It's taking ages. And C is old. It's a very old language that basically kind of like set the standards for how we kind of program today in most of the common programming languages. There's different ones, don't get me wrong. But C set a lot of the like standard crap. So let's just say, I'll make it C++, but really it'll just be C. All right. What this is here that I'm using is an IDE, Integrated Development Environment. Colab is kind of like one for Python. There's another really popular one that's more like this, the one I'm using that runs on your computer called PyCharm. If you're interested, start playing around with PyCharm if you think you might want to use like an IDE. Anyways, here is C++. So int main, if I run this, it'll say hello world. Hello world. Great. So I know it's working. So here's what I'm going to do. I'm going to create a new integer array called my array of size 5 equals, and I'm just going to hard code it as A, B, C, D, E. Can you see this at the back? I realize it's small. You can't really see it, eh?
I can't read individual letters, but see what the
Let's see if I can.
yeah. With the black background, everything's
Let's see if I can change the settings to settings. Okay, that's, well, yes, but perhaps a little much, but whatever. We can deal with this, okay? And I'm going to write a for loop for int I equals 0, I is less than 5, I plus plus. And then, because I'm lazy, don't worry, this is C or it's C++. This is not on the test. Do not worry. So here's what we're going to do. I'm going to print each thing out. Okay, stop telling me. So I'm printing out the array A, B, C, D, E. What? Oh. No, I printed out hello world 5 times. Even though you've never seen C++ before, I'm willing to bet that this code, I should make this a character. I'm willing to bet that this code actually makes sense to you. You see 4. What should you think? Loop. Exactly. All right. So first of all, actually, interesting thing you might see, I made the string or the array A, B, C, D, E. They're characters. Yet it printed out 97, 98, 99, 100, 101. Why? Well, they're the numerical values of the letter, and I actually made my array type int. So it's just like, I know you wrote a character, but you totally meant int because you said int. So I should do char, there. Now if I run it, yeah, run. A, B, C, D, E, great. So this array is size 5, and you asked an interesting question of like, well, how does it know when it's done? It doesn't. See what happens if I do 10. Run. Okay, it's running fine. A, B, C, D, E, and what it did is, you know how I showed you, it said like go to memory address 677. And I had 5 things in it. It did +0, +1, +2, +3, +4, +5. And it told me what the zeros and ones in that memory address mean. As a character, or it tries to at least. That question mark doesn't mean the character question mark. That means like something weird happened. So in this older programming language, it's saying like, yeah, you totally meant to do that, right? Because you wrote the code. How many times have you used a list and it said index out of range error or something? Yeah. Well, I just did that. But it didn't care. It's like, yeah, here you go. Who here thinks that's fun? Who here thinks that's annoying? It's annoying. So, even more weird, now this is a big no-no. Never, ever, ever do this. I'm going to say, if I say my array at index 2 equals 88, which I realize is an integer, but let's see what character it pops up as just for fun. It's capital X, I guess. Whatever. Now, what do you think is going to happen if I do this? First of all, wait, is it saying something funny to me? It's giving me a warning. What's the warning? The IDE, the Integrated Development Environment, is giving me a warning saying, But that's not the programming language. The programming language is just going to do what you tell it. The IDE is like the person you're talking to that communicates with the programming language. And this person's like, I don't think you want to do that. But let's do that. Actually, let's not do 12. Let's do 7. Because we'll print it out. Whoops. Run. It's there. Look, we got the X. But I said make an array of size 5, and the computer said, okay, I'm going to go find a chunk of RAM of size 5 for your information. There you go. And then you said, okay, now change over here. If you do this, this is risky, 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 risky. It's not even risky. It is absolutely a terrible idea to do this. Because now we are modifying RAM that we never actually allocated for ourselves. If I started getting crazy here, on my computer in RAM, I have all the information needed to run my operating system. Valuable information that needs to be set a certain way. If I do this, I can start messing with values that are already loaded in RAM that I need for my operating system. Anyways, I'll see you later.